So the topic I will present today is cognitive media access, an optimal learning approach. This is a joint work with Professor Hanshin Ackerman from Ohio State, from Professor Jiang Hai from University of Alberta, and Professor Vincent Poole from Princeton University. As a disclaimer, my main research field is on the information theory. So like as you know, for people who work on information theory, we like closed form solution. So also in this work, we make some assumptions in order to the problem to be checkable. So maybe the assumptions may not be so realistic, but anyway, this is our first step to build to the practical solution. So maybe the results here can serve as an upper bound of any practical system. So now let's start. So here's the outline of this talk. In the background part, I will introduce what I mean by cognitive media access. Then in a single user case, I will describe our results for the case where there's only one cognitive user who try to use the spectrum. We derive some optimal solution, and we also derive some low complexity or the optimal solution. Then in the third part, I will move on to the multiple user case, where there are several cognitive users compete with each other for the limited resource. And finally, I will give some conclusions and point out some future directions. So as you know, that because of the development of wireless applications, almost all the frequency bands have been occupied. But on the other hand, based on real-time measurements, the spectrum is underutilized. So this figure shows is the spectrum allocation by FCC at American, and this figure shows is the real-time measurement at the UC Berkeley Wireless Research Center. In this figure, the orange color represents radio activities. So, and the green color means there's no activity. So as we can see here, that a lot of empty spaces here, and also the level of activity depends on time and also depends on the frequency domain. So the main idea of cognitive radio is to reuse the spectrum. So there are several different ways to do that. One is ask the cognitive transmitter to use very low power over a large band. The other approach will be ask the cognitive radio to transmit when the primary user is not transmitting. So in this talk, we will use the second approach. That is, the cognitive radio can only transmit when the main user is not transmitting. Of course, in order to make this technique useful, there are a lot of issues we need to solve before this technique will be accepted by the industry. I think the professors at WINLAB has done a lot of interesting work here. So in this talk, I will only focus on media access of the cognitive radio, the so-called cognitive media access. So the main difference between the cognitive media access and the media access we were talking is that in the cognitive, because of the primary user. So in the cognitive radio, there are high priority cognitive primary users. The cognitive user can only transmit when the primary user is not transmitting. So here's the problem setup. We have n channels, 1 to n, and each channel is free with certain availability structure. For example, maybe whether a channel is free or not may follow the Markov chain or RID anyway. So there is some structure in the time domain, and due to complexity constraints, a cognitive user can only select a subset of channels to access at each time. So if a channel is free, then if the channel this cognitive user select is free, then it can send b bits over the channel. If the channel it selects is busy, then it cannot send anything. So the main question is how will the cognitive user select the cognitive user need to decide which subset of channel to sense at each time slot in order to maximize its own throughput. So that was some existing works. So in a paper published by a group at Rice University, they assume that the channels are always available. But on the other hand, the number of bits you can transmit over the channel depends on the channel gain. So the problem boils down to finding a channel with good channel gain. In this case, they use a stopping time approach to solve this problem. And there's another group at UC Davis and Cornell. They assume that whether a channel is free or not follows a Markov chain. The main assumption is that the transition probability is known. So in this case, the problem becomes a partial observable Markov chain. They use that approach to solve the problem. And in our work, we focus on the case where the free probability, whether a channel is free or not, we don't know this probability. The main reason for this is that because the free probability of each channel depends on the activity of the primary user, which is highly dynamic. You can think that the activity of the main user may be more active during the day, maybe like slightly idle during the night. So it's not too realistic to assume that the cognitive user knows this probability precisely. So now let's move on to the single user case. So in this part, we will derive some optimal solution. We will also characterize the cost of learning. And then we will derive some low complexity order optimal solution, and we will consider more capable cognitive user. So in the first at the beginning, I will assume that the cognitive user can only select a single channel, and later on I will consider the case where cognitive user can access more than one channel. So here's the assumptions. As I have mentioned, we assume that whether a channel is free or not, the probability of whether theta I is unknown. We don't know the parameter, and we assume that this theta is fixed for t time slots, and change to another value with density f theta. So in some sense, we can think of this theta as a channel gain of a fading channel, and this f theta as the density of the fading gain. But there's a big difference between theta and the channel fading gain. So we know that it is relatively easy to estimate the fading gain. But here, if we want to estimate theta, we need to spend some time on it. But since the theta is only fixed for t time slot, after you estimate the channel, maybe the time is over.
I is the index of the channel?
Huh?
I is the index of the channel?
Yeah, I from 1 to n. So we don't know the value of that. Okay. So we assume that once a theta is fixed, then the channels are independent across time. Certain results can be extended to the Markov case, Markov chain case, but we are not going to study that here. We assume that sensing is perfect, so there's no sensing error in the physical layer, and we assume that transmitter and receiver channel. We will study the case where sensing is not perfect later, but not here. So now here's the optimization problem. So the cognitive user have a strategy gamma, which that will pick one channel to sense at time j, based on the information it has learned through sensing. So here S1 is the channel the cognitive user picked, and ZS1 is a Boolean random variable, which equals 1 if the channel is free, equals 0 if it's busy. So the cognitive user can make his decision based on the information it has learned before. The optimization problem is the cognitive user try to send as many bits as possible in the t time slots. So BZSJJ is the bits it can send at time slot j. remember that if the channel is free, this is 1. If channel is busy, this is 0. Okay, so this is the total number of bits it can send over the t time slot, and the cognitive user try to maximize the expected value of this term of this summation.
So the channel condition now
here we assume that if channel is free, we can send b bits. So the b is fixed. We do not know the we do not care about the channel gain. We assume that whether it's free or not is RID, so there's no way you can predict.
Okay.
Yeah, but some results can be extended to the Markov case. In that case, you can predict, but in the RID case, you cannot predict.
Okay, so through this vector that you have, you said you're trying to...
Yeah, through this vector, you can estimate a set, right?
Okay.
Yeah, in this case, you have some sense which channel is better, which channel has a larger chance of getting free.
Okay, but you'll only transmit when it's free.
Yeah. So the problem is you based on the information you have learned, you can estimate the channel, right? Then you decide which one to sense.
Okay.
If it's free, then you can send. If it's not free, you cannot send.
So at the beginning of a slot,
you make a decision to go for which one?
So you already decide at the beginning of the slot whether you want to go for that slot or not.
Yeah, yeah.
Right. Whether it's, but you don't know for sure whether
No,
it's going to be free.
no. You need a sense. You need some time to sense.
So you need some little bit of guard time to sense.
Yeah,
whether it's
yeah, yeah. And Project, what's your question?
I was just like, psi is your like a pairwise, whereas S1 is what you're sensing, and Z is whether it's free.
Yeah.
Okay. And they're all independent pairwise. And
this is a pairwise, yes.
So, I'm sorry. Why can't you do this sensing at the beginning of the time slot for every slot in every channel?
This is there are several reasons. Like the first one is complexity, and the other one is you need some time to make decision. I mean, detection is not perfect. You cannot just go there and get whether it's free or not, right? You need some. I mean, in order to get a precise detection, you need to spend a lot of time. Some time, yeah. There's a lower bound on that kind of thing.
But you're taking the expected value of that whole thing, right? The E means the expected value of the whole thing.
Yeah, expected value.
And what about the W?
This one?
Yeah.
This gamma is the strategy you will use. So this means the throughput will use by this particular strategy. I mean, your decision will depend on this strategy, right? Which channel you will go depend on this strategy.
So explain that to again.
Gamma is the strategy, the particular strategy you will use. And the W gamma is the throughput you will get by this particular strategy. Now the question is, what is the optimal gamma? You want to optimize this term.
you decide on gamma in advance. I mean, on S in advance.
And then this gamma you can depend on the information you have learned.
So recursively?
Because I mean, whatever whichever, I mean, whatever you like to do. Huh? I mean, it need to be causal. This is the only limitation. Causal, yeah. Only based on the information you know. You cannot predict. You cannot based on the information in the future.
You think what is F?
F. So as you may remember here, so we assume that this theta is fixed for t time slot and change it to another value based on this density F. So maybe related but maybe more interesting problem is the following. You go to a casino, that N machine here, and if you play a machine I, you will get $1 with probability theta I, okay? And you don't know the value of theta. Each time you are allowed to play one machine. So what we will do in order to maximize the number, the money you will get. So you go this machine, you get $1 with a certain probability. You don't know this one, and what we will do to maximize the number of money you will get, like in a fixed number of plays. So there were some heuristic schemes, like simple heuristic schemes. The first one is random selection. You just randomly choose a channel at each time slot. So with this scheme, you are guaranteed that you will pick the best channel with positive probability, right? There's only n channels, and if you randomly select, I mean, you will always go to the best channel with certain probability. But you may also end up with bad channels. So the second one is called a myopic scheme. So you will always choose the channel with largest estimated free probability, because based on history you can estimate the value of theta, and you can, in this scheme they always go to the channel with the largest estimate free probability. And here is also another one called stay with the winner and switch from the loser. So in this case, you will choose the same channel if it was found to be free in the last time slot, and switch to another channel if it was found to be busy at last time slot. So another one is called epsilon greedy strategy. So in this strategy, you will choose the best estimated channel with probability epsilon.
Do you also assume that you're estimating the value of capital T, or you just assume it's known?
Capital T is known.
Is known.
Yeah.
Okay. So when you say using the past history, you use only the most recent T.
Yeah. Most in this block, okay. Because in the former block the value of theta has been changed. Sure. That's no value for you. So all these strategies seems like there are several reasoning behind these schemes. So in some sense, all these schemes make sense. But as we will show later on that there's a big loss compared with the optimal solution of these schemes. So now let's try to solve the optimization problem. So for each decision you make, there are two gains. The first one is called short-term gain, which means the immediate transmission opportunity you will get if the channel is found to be free, right? And then the other one is called the long-term gain. Because after you make a sensing, you can estimate, you learn the statistical information about free probability. This information is very useful for you to make future decisions. So we call this delayed reward. This is immediate reward. This is delayed reward. So it is easy to see that a good scheme should strike a balance between these two, between this exploitation and exploration. So by exploitation, I mean that you try to use the information you have learned. So in this case, if you want to maximize the exploitation, you will go to the best. You will go to the best channel. But on the other hand, if you want to maximize your long-term gain, you need to choose some bad channels intentionally in order to obtain a final estimate. So optimal strategy should have a good balance between these two gains. Now let's play around with a smaller with a smaller problem first. Is 1. In this case, we don't need to worry about the future gain because the value of theta will change anyway. So the information is there's no value to care. You don't need to care about the long-term gain. So so you can always choose the channel with the largest expected gain. Okay. So for t equal to 1, the optimization problem is easy to solve, and in the following we use this notation. So V star means optimal, F is the density, and the 1 is the means t equal to 1. Now what about t equal to 2? What about t equal to 2? So at the beginning of the first time slot, you need to decide which channel to go, right? You need to decide which channel to select. So let's see. If you choose channel I at the first time slot, and free probability of channel I is theta I, one of the following two things will happen. So the first thing is like you found channel I is free. Channel I is free, okay? So this happens with probability theta I, okay? So if channel I is free, you will have immediate throughput, which is b bits. And using Bayes rule, you can update the density function. Okay, and this is the Bayes rule. You can update the function. Now the question is what you will get in the second time slot. This is so at the end of the first slot, there's only one time slot left. So this problem becomes a t equal to 1 problem again, with only update with update density, right? So this is the expected long future throughput. This is a t equal to 1 problem, and we know how to solve it. Okay. So this is the immediate throughput you will get in the first time slot, and this is the future throughput. Similarly, if channel is busy, then this will happen with probability 1 minus theta I. The immediate throughput is 0. And update information using Bayes' rule. And future throughput, again, this is a t equal to 1 problem, and we already know how to solve it. Okay, so in summary, at the beginning of first time slot, if you select channel I, this is the expected gain you will get by making decision of I. So the optimal solution will be in the first time slot, you will try to choose a channel that maximizes this, that has the largest value of this expression. And based on, now for t equal to 1 problem, to 2 problem, we know that what you will do at the very beginning. And at the end of the first sensing, the problem becomes a t equal to 1 problem, and we already know how to solve it. So now the problem for t equal to 2 is already solved. We can go over in a similar way. Like now we know how to solve t equal to 2 problem, and then we will know how to solve a problem t equal to 3, and so on. So in general, so the problem can be solved in this recursive way. So this is what you will do at the beginning of the first. Will select channel that maximize this term, and at the end of first time slot, the problem becomes a t minus 1 problem, and we already know the solution. Okay, so. So we can see that the solution of this problem has a dynamic programming flavor, but there's a big drawback of this approach. The complexity is really high. It grows exponentially with t. So later on, I will give a scheme that have very low complexity and it's order optimal. But before we do that, let's look at the performance limit of this optimal solution. So compared with the case where if the value of theta is known, you will always pick the best channel, right? And so this is the throughput you will get if the value of theta is known. But now, since you don't know the value of theta, you will end up with some bad channels. So this is the throughput you will get in a t time slot. So the difference is the cost of learning. So you spend some time on learning the value of theta. So you go to some bad channels, and this is the cost. So we would like to see how will this cost scales with t in the optimal solution. So we we will give some definition. We call strategy to be consistent if the cost of learning grows slower than grows sublinearly, which means that there exists a bit which is less than 1, so that the cost of learning grows slower than order t to the power bit for any theta. So in order to help you to understand this definition, let's give a simple example. In this example, we call it a royal strategy. So in this case, the transmitter will always select channel I. Okay. So now, if channel I is indeed the best, then the cost of learning is 0 because you are right. You always go to the best channel. But on the other hand, if channel I is not the best, then the cost of learning scales as t, because you are always selecting the bad channel. Okay. So we can see that this scheme is not consistent. Sometimes it's good, sometimes it's bad. We need a scheme that is universally good. So here's a lower bound of any consistent scheme. So we can show that for any consistent strategy, the cost of learning scales at least as order of log t. So here D is the divergence between two Bologna random variables with parameter theta I and theta I star. And theta I star, as I mentioned, is the best channel. So you can intuitively you can think of each term as the number of samples you have to take for the bad channel in order to distinguish the bad channel and from the best channel. Okay. Yeah, this is the intuition. You need to spend at least a log of t time on the bad channels in order to make sure which channel is good and which channel is not the best one. So we also give a definition if a scheme is order optimal if the cost of learning scales as order log t. So let's look at the cost of the schemes. The cost of scheme I have mentioned. In a random strategy, because you select each channel with probability 1/n. So most of the time you are spending your most of the time you are selecting a bad channel. So the order of loss is t. And in a Maomic strategy, you can also show that the order of loss is also t. And for the stay with the winner, switch from the loser, we can also show that the loss is scaled with order linearly with t. This is not so obvious, but we can show that. And for the epsilon greedy strategy, it is also order of t, because you are spending 1 minus epsilon time on the bad channels. So it will scale with t. So that none of these is order optimal. Although it makes sense, but it's not order optimal.
So your L somehow measures the distance between, in terms of time, in terms of what's the measure? I mean, there's a distance between the
where? I mean here. Here?
Like if you knew the theta, right?
If you knew the theta, you will always go to the best channel, right?
Right.
So this is but if you don't know, you will spend some time on the bad channels.
Right.
Yeah. So there's a difference between these two performance. This is we call cost of learning, and we want to know how this scales with t.
Okay. And can you show us the L definition of L again?
The definition. Here. This is the throughput you will get if you know the value of theta. This is what you will do. You spend some time on the bad channels.
Right.
Your summation over all of them. Okay. And we want to know how this scales.
So it's a throughput measure.
Yeah, throughput. Yeah.
By calling it order optimal, by calling log of t order optimal, are you implying that that's a lower bound on the? So
let's see. So this is the lower bound for any scheme. This is for any consistent, for any universal good scheme. So this is the lower bound. If you have scheme achieve this lower bound, this is order optimal, right?
And somehow when you express that as a function of t, you're saying I don't want that to scale with t, I want it to scale slower than?
Slower than t, yeah. So we want to scale sublinear. If you scale linear, then you can do any scheme will scale as linear. You can do anything, right? You want to do the best, so you want to get a good throughput. So the lower bound is log t. You cannot do better than this.
The actual expression log t, how does it come about? Does it come from? I mean, you haven't shown that, right?
You mean no? This is a lower bound. I will give a scheme that achieve this later on.
How do you figure out that that's the lower bound?
This is the proof from the proof.
Okay, from the proof.
Yeah.
Just not here.
Not here. No, I will not talk about the proof here. Just give some results. Yeah. So here, all these schemes are not order optimal. So now let's come to a low complexity order optimal scheme. The scheme is very simple. At the beginning, you will sense each channel once. Then, in the following time slot, you obtain an estimate of the theta by xij divided by yij. Here, yij is the number of times you have select channel I, okay, and xij is the number of times you found channel I to be free, okay. So this is just a simple estimator. This is the time you found it's free, and this time you have tried. So this is estimation, and you assign an index gamma ij by adding the estimate another additional term here, 2 log j yij. This if you do not have this, then the source will choose the channel with the largest index at time j. Okay, so if we do not have this additional term, then this scheme is myomic because you will always choose the best estimate. But now you have an additional term here. Okay, so I will explain why we add this. Okay, so we can show that the cost of scheme scales as order log t. I will show the reason in the next slides, but here we can see that the scheme is non-parametric. We don't need to know the value of f state, and it's very simple, and the complexity does not increase with t. Remember that the optimal solution, the complexity grows exponentially, but here the complexity is the same no matter what's the number of t. Here's the reason. Here's the intuition behind the scheme. So let's look at this term. Okay. So if yij is large, if yij is very large, then the estimate is good, right? And also we can look at this index. If yij is large, then this term is small. So the index will be determined by the estimate. So we will end up with choosing the best estimate. So this leads to exploitation. Okay, so if yij is large.
Yeah, I get that, but why did you put how did you know you have to put 1 upon square root of the number of times you've tried?
Is the idea that your estimate is only good if you have observed it for a long number of times?
Yeah.
So if you have observed for a long number of times, then you have a good estimate. Then automatically your gamma ij is equal to theta ij. But if you observe only for 2 times, let's say yi is 2, then your estimate probability is not going to be that good.
Then the index will be determined by the
That's the main idea.
Yeah, this is the main idea. Yeah. So if this one is small, then this estimate is not good. But look at this expression. If this one is small, then this one is large. Then your index will be determined by this one. Then you will go to the channel that you have not selected enough, right? This log j here is comes from the lower bound because
J is the time slot index.
Yeah, j is time slot. I is the channel slot.
And you're assuming this is basically Gaussian, random.
This is Brownian.
Okay, but what about time series correlations? Like every day at noon, the channel's full.
You mean the Markov chain case?
Yes.
This scheme will not work for the Markov chain case, but the results. We are working on that, and we have some. There's hope that we can also design some simple scheme for the Markov case, but this scheme only works for the IID case.
Right.
But maybe in the
real channel utilization, what it actually looks like, is it more independent or is it more Markov chain?
I think Markov chain will be more realistic. Yeah, but as I know, like in order to get some solution, we solve the simple problem first, and then we will go to the complex one later. Okay, so now we have so until now I only studied the case where the user will only try to select one channel. Okay, so what if the user can select more than one channel? Now here's more this. So here we assume that still the user has a strategy that will select a set of channels to sense based on the information it has learned. And similarly, the optimization problem is like this. Try to optimize the total throughput it can obtain in a t time slot. Same as a single user case, we can get optimal solution based on dynamic programming, and the complexity grows exponentially with t. So this is not desirable in real application because it's too complicated. Similarly, we derive a lower bound on the cost. So this is what you will get if the value of theta is known, right? So you have m theta. So here I order the value of theta by theta 1 is the largest and theta n is the smallest. Okay. So here is what you will get by knowing the theta, and this is what you will get by in a case where you don't know. So this is the cost of learning, and we can show that the cost of learning scales as log t. So
I'm a little confused about this. The function L. You're saying that the difference between the best case throughput, if we knew theta,
yeah,
and the case in which we're using our past history
yeah,
to learn theta,
yeah,
is of the order of log t.
Log t, yeah.
Or in the other cases is the order of t. So
Ye-
if t is large, then this difference is large.
Yes, yes.
That seems to be counterintuitive, because if you have a larger t and you have more history to learn from, then the difference between the ideal and your learning case, shouldn't it go smaller? Or am I missing something here?
Okay, so like if t is large,
Yeah.
you can do this. I mean, sometimes what you are talking about, you spend some time on the beginning, right? In the beginning and estimate the theta. Then in the later on, you will always go to the best channel, right? This is what you are talking about. So the basic idea is like as t, no matter what's the value of t, you need to spend log t on each channel to make sure that the estimator you have is truly the best.
Okay, this order of log t, is it characterizing L, or it's characterizing something else?
Characterize L.
It is L, right?
Yes, it is L.
So this difference in the two terms,
Different.
why is it growing with t? I don't understand.
Okay, so the basic idea is like this. So as t increase, you need to spend more time on the better channels. If you spend fixed time on the better channels, although you have an estimator, but the estimator will not be good. You cannot make sure that the estimator is good. Maybe if you spend fixed time on the bad channels, there's a chance that you are going to the bad channel. Okay, so here's an order optimal, simple, complex, low complexity scheme. And similarly, you will obtain an estimate and assign an index. Now, what you will do, you will choose the channels with the largest m index. So in each case, you can choose m channels, and in this case, you will choose the m largest index. So this is we can show that this is order optimal, and the basic idea is still the same. We can bound the number of samplings on the bad channels.
Optimal number of how many channels you sample?
Or it should grow with log t. You mean you are talking about the constant before the log?
No, I'm saying like here you are sampling a subset of the initial m channels instead of 1.
Yeah.
So is there an optimal number of channels if you sample?
Oh, here m. Oh, m is no. In the beginning, I assume that a user can choose m channel at each time.
Yeah,
So m is fixed. Hmm?
Is there some optimal value for that m?
Oh no, I mean, if you can choose m, obviously you can m should be the n, right? Yeah, and larger the better, because you have more chance to get all the channels. So the question is here is if the m is fixed, what's the best you can do? Okay, so now let's move on to the multiple user case. So in a multiple user, there's another dimension of trade-off. In this case, it is not optimal for all the users to go to the best channel anymore, right? Because if all of them go to the best channel, the channel in the other, the opportunity in the other channels will be wasted and there will be too many users competing in the best channel.
So multiple cognitive users.
Yeah, I'm talking about cognitive users. Yeah. So in this part, I will discuss. We will first discuss the case where the value of theta is known. Let's see what we can do here, and later on we will discuss the case where the theta is not known, and what you can do to approach the performance you can get when the theta is known. Okay, so so in order to simplify the analysis, we assume that the user will follow the following protocol. So let's see. At time j, let Kij be the set of users that choose to sense channel I. Okay, so this is the set of users who will sense channel I. Now, if channel I is indeed free, okay, if channel I is indeed free, then the users will will go the following protocol to take control of the channel. So each user will generate a random number Tkj and wait this period. At the end of waiting, each user will sense again, and if the channel is still free, then the user will take control of the channel. Okay, so basically the user who generate the smallest random number will take control of the channel, and the optimization problem is the user try to maximize the throughput it can get. So this indication function means the user actually take control of the channel. And this is whether the channel is free or not. Okay, so we have this additional term here. So as I have mentioned, even if we assume theta is known, it's not optimal for other users to sense the channel's largest theta I, because in this case, there are too many users compete for the same channel, and opportunities on the other channels are wasted. So what if there's a centralized controller? If there's a centralized controller, the problem is also easy. I mean, if here k is the number of users, n is the number of channels. Okay. So if the number of users is very large, then the centralized controller can assign at least one user to each channel at each time slot. So in this case, you can take all the transmission opportunities. Okay. If the number of users is not large, then you can assign the k user to the best k channels. I mean, so for the centralized scheme, the problem is really easy. But we are.
Excuse me, are you assuming that all the users have the same need? Do all the users need the same amount of bandwidth?
Here we are talking we are interested with the sum rate, the throughput, the sum of the throughput you will get for the total network.
Okay.
If we do not care about the QoS, no.
But some users might not need unbounded bandwidth. They might need only a certain amount of bandwidth for their application.
Yeah, that's true.
So you could pack two into a channel if the right size channel.
Yes, that's true. But
I mean, if there's a voice channel, for example, or packet voice or something.
Yeah, that's definitely true. But here we only focus on throughput, so we haven't incorporated the higher level things yet. But here we only care about the throughput. But what you have said is definitely true. Yeah.
But is there some bound on the individual users?
No, they only want to maximize
one user going into a very broadband channel and the others being locked out.
And the other, a lot of bands. Here, each band is a small band.
Okay. You're throttled by the band size. You're limited by the band size.
Yeah, the number of bits you can transmit is limited by the bandwidth. This number of B. Yeah, the B is limited by the bandwidth. So we are interested in the distributed schemes. Here's a particular one we are interested. We assume that the users will follow a symmetric strategy. By symmetric, I mean that each user will choose each channel with a certain probability. So let's use P as P1 to Pn. P1 is the probability that each user will choose channel 1, and Pn is the probability that the user will choose channel n. So we want to know the optimal value of this vector P. We can do the following things. So the first thing we know that with a centralized scheme, we can get all the transmission opportunities. Okay, so if we have a centralized scheme, this is what you will get. Okay, so but with this particular strategy, this is with this particular strategy, there's a loss compared with this centralized scheme. So if we assume that each user will use this vector p, then this is the loss in terms of total throughput. I mean, this is very easy to understand because 1 minus pi power k is the probability that none of the user is choosing channel I, right? So this is the loss of this particular scheme. And then if you want to know the optimal value of p, then you only need to minimize this L. You only need to minimize this loss.
Excuse me. This is a question related to what you were saying. I don't think you're worrying about system throughput, but the thing that you're trying to control is the channel access probability.
Yeah.
You're not really concerned about what offered load the channel access probability is what you're trying to control, right?
Yes.
That's it.
Okay. Yeah. So the thing is, like, if the strategy is symmetric, okay. So if you maximize your total throughput, then the throughput of each user will also be maximized, right?
So the assumption is every user wants the same amount.
Yeah. This is our assumption.
Right.
Yeah.
So it doesn't take.
So this is a very this is a easy optimization problem. I mean, the function is convex in a region where we are interested, and so we can solve the optimization problem. I mean, the optimal p is given in this equation. So there's a certain drawback here. So as you can see here, okay. So now what is the so compared with the centralized scheme, we can show that with this particular symmetric scheme, the loss goes down to 0 exponentially. So here Q is the number of the channels that are not always busy. So the decay rate is given in this equation. So there's a certain drawback in this approach. The first one is like this pi depends on the value of k, which means that each user needs to know how many cognitive users are in the network. So maybe, but in a real life, users are coming and going. So maybe this is not a really realistic assumption. The other one is like why the users, I mean, the other one is this scheme may not be robust because people may think, okay, if I do something else, I can get better performance. So this scheme is not robust. So in order to derive some robust scheme, we can also consider a game theoretical model. So we consider the following channel selection game. The players are the cognitive users, and the strategy are the same as before the channel selection strategy. And the payoff is what each user can get in throughput. Okay, so here's the definition of Nash Equilibrium. This is a very standard definition. So this game actually this game is not well defined. So there might be a lot of Nash Equilibrium. Okay, so but following is a particular. We show that if there are tau ik users sense channel I at each time, where tau I is given in this equation, then this particular strategy is a Nash equilibrium. Okay, but in order to work at this particular Nash equilibrium, we need coordination among the users because we need to make sure that this amount of users at each time slot at each channel. So although this is Nash equilibrium, but this is not a practical solution. We need coordination among the users. So, but on the other hand, we can have a simple scheme to make sure that the users will work very closely at this Nash equilibrium. Okay, so the strategy is each user will choose channel I with probability given in this equation. Okay, so this is the reason why we choose this is if you look at the average number of users who choose channel I will be the same as we're given by this the average number of users who will select channel I is given tau ik. So we show that the performance loss of this operating point also goes to 0 exponentially. But decay rate is smaller than optimal symmetric scheme, but it does goes to 0. So the advantage of this scheme that we don't need to know the number of users k in the network. So it's more. The other thing is more robust because this is Nash equilibrium. If you do something else, maybe your throughput will be less. Okay, so now, so let's move on to the unknown parameter case. So we know that if the theta is known, we have this optimal symmetric points. We also have this approximate Nash equilibrium. Now the question is, if the value of theta is unknown, can we design simple schemes that converges to this 2 points? The answer is yes, and the scheme is very simple. So let's first come to the Nash equilibrium point.
Let me answer this conceptually. You want this to be a distributed solution, right?
Yeah.
Do they make the solution choose it in advance?
What do you mean by in advance?
Well,
I mean they will choose a channel.
Your strategies P, right?
Yes.
Are same for all of them.
That's for the symmetric case. Yes.
Symmetric case.
Yeah.
Okay, so symmetric case.
In the symmetric case, we assume that each user will use this same symmetric case, but this might not be true. So then we come to this game theoretical model. They can do anything, but this is Nash equilibrium. So this is of your own interest to go for this strategy, right? So now let's assume that the value of theta is unknown. How can we design a scheme that will converge to this Nash equilibrium? So we have so each user k will maintain 2 vectors xk and yik. Here yik will remember the number of times I have selected each channel, and the xk will remember the number of times the channel each channel is free. Okay, so in the initialization part, each user will sense each channel once at the very beginning and set xki as 1, no matter whether the channel is really free or not. And in the later on, in the later time slot, the user will first get the estimate. So the estimate is the same as before, xki divided by yki, and then the user will select channel I with this probability. So this probability is only dependent on the estimator. Okay, so after sensing, the user will update xk and yk, and if channel is found to be free, then the user will follow the protocol I have described. So we show that this simple scheme converges to the approximate Nash equilibrium. The main reason following are the main reason for this scheme to converge. Remember that if theta is known, then if a user select channel with this probability, then the users will work approximately at this Nash equilibrium. Okay, so we show that with this particular strategy, the number of times each user will go to channel I increase linearly with t. So which means that each user will select channel enough number of times, so the estimator, the theta hat, will converge to the true value of theta I. Okay, then the probability vector p will converge to the optimal value. So this is the main idea of this convergence. So similarly for the symmetric optimal scheme, we have this simple scheme. The initialization part is the same, the estimation is the same, and only the channel selection probability will be different. So you can remember that this form has the same similar form as the symmetric case when the value of theta is null. Only difference here is that we use this estimator. So we also show that this scheme converges to the optimal symmetric operating point. The proof is similar. Like we can show that each user will go to each channel enough number of times. Then the estimator will converge to the true value. Then this pi star will converge to the optimal point. So here is the conclusion. So we consider the media access control with unknown free probability. We developed some optimal strategy. We characterize the cost of learning, and we design several low complexity order optimal schemes. So for the future work, we can include the sensing error. So in this talk, we assume that there's no error in the sensing, and we need to consider the delay limited scenario, because the whole idea is between trade-off between this long-term gain and short-term gain. But in a delay limited scenario, maybe this long-term gain doesn't make sense anymore. So we need to consider this case, and we also need to consider the opportunistic transmission. So as the question by Xiaojun, so here we consider B is fixed, but actually the B depends on the channel gain. So what in that case, what is the performance? We can consider that, and we need to consider the Markov chain case. That's all. Thanks.